let's start with some kinematics. We're mostly starting with kinematics because what we really want to do is start with some calculus, and kinematics is a good way to do that. So let's start. So kinematics. We've taken physics before. Could you please stop? Write down every kinematics equations you remember from last year. Let's have a look. Okay. So these are our equations from last year. Do you remember these? Are these the equations you remember? And did you get the squares right and the factors of 2 and 1/2 and the final velocities versus the initial and all that? Check if you got them right. Now, it's important to know the difference between an average and a final velocity. So the average is when we put a little bar over top. An average is the difference between an initial and final position divided by time. So an average velocity is the final displacement divided by time. And so that would be the final displacement minus initial displacement divided by the amount of time. And an average acceleration would be the final velocity minus the initial velocity divided by the amount of time. Okay. We're just reminding you that. On a graph, the average velocity on a displacement time graph is the slope of the line connecting two different points. So we want an average velocity, slope of the line, that'll give us an average velocity. And how about from a displacement time graph, the instantaneous velocity? Well, that's the slope of the tangent line to that particular point. That red line is tangent to that graph at point B, so the instantaneous velocity at point B is the slope of that tangent line. Here, if we have a velocity time graph, the slope of a line will be an acceleration. The slope of the line connecting A and B will be the average velocity between A and B. And the slope of the line of the tangent at point C is the instantaneous acceleration at point C. Those two things are different. The average acceleration between A and B is different from the instantaneous acceleration at C. So let's have a look at this. If we have a graph, it's a displacement time graph, so the slope is going to be velocity, and change in velocity is acceleration. At what point or points is or are the accelerations 0? Possible answers are 1 and 4, 2, 3, or none of these points, or some other combination. So, well, the answer is we're looking for a 0 acceleration. The answer is 2. Why is that? Because the velocity before the point 2 and the velocity after point 2 are almost exactly the same. The velocity of a displacement time graph is the slope. The slope really didn't change. So it's point 2. Now, same graph. What about a positive acceleration? At what points are we going to have a positive acceleration? 1 and 4, 2, or 3, or none of these points, or some other combination. And the answer is you have a positive acceleration at point 3. A positive acceleration means that you have a positive change in the velocity. Just before point 3, you had a negative slope, a negative velocity. Just after the third point, you have a positive slope, a positive velocity. So the change in your velocity is positive, which means your acceleration was positive. How about, we wait just a second while this loads. How about a negative acceleration? At what point or points is the acceleration negative? And the answer is it's negative at, the acceleration is negative at 1 and 4. We have a displacement time graph. The slope of the graph is velocity, and the change in the slope is our acceleration. So at point 1, we started with a positive velocity, positive slope, and just after our point, we have a negative velocity, a negative slope. So that change in the velocity is negative, and we have a negative acceleration. Same for 4. Started off with a positive velocity, ended with a negative velocity. That change in velocity, change in slope is negative, so it's a negative acceleration. Great. This just explains it. When you have a concave down, the instantaneous acceleration is negative. If you have a concave up, you have, so that's down. If you have a concave up, you have a positive acceleration. And if you have a constant slope, you have zero acceleration. This is for a displacement versus time graph. So here we go. What about if we have air resistance? So we've got an object, we're dropping the object from rest, and it reaches terminal velocity during its fall. What would the displacement versus time graph look like? So we're starting off with some positives, we're up in the air because we're dropping this object, and we're going to drop the object and it's going to reach terminal velocity. What does that look like? Well, here we go. We started off with a zero slope pretty well. So that's a zero velocity. When you drop something, it has zero velocity. It goes faster and faster and faster. So a steeper and steeper and steeper slope until terminal velocity, the slope is constant. There's no more change in the velocity, which means that the terminal velocity was constant. You had reached terminal velocity. Cool. How about that same object? If you started off with an object, you drop from rest, it reaches terminal velocity, what would the velocity versus time graph look like? And I'm going to say that we're going to consider up to be positive and down negative. So if you have a negative velocity, it's going to be a negative. If you're falling downwards, it'll be a negative velocity. So what does that graph look like? Oh yeah, here we go. So we started at a zero velocity. When we first dropped our object, it was at a zero velocity. And we ended at a constant negative velocity. So we ended at a terminal velocity. And we had a changing acceleration. Look, we started off with, I'd say a 9.8 meters per second squared acceleration downwards. And then it got more and more air resistance and less acceleration until finally we ended up with a constant velocity, terminal velocity. What about the acceleration? What did the acceleration look like? You're dropping the same object from rest. Let's consider up as positive, down as negative. So a negative acceleration would be downwards. That acceleration, I believe, was changing. So what is that going to look like? Graph that now. And here we go. We started off with a negative acceleration. Probably negative 9.8 meters per second squared. And when we reached terminal velocity, we had zero acceleration. So in fact, we could continue this graph for a while with a zero acceleration because we had terminal velocity, no more acceleration. And that is it. Ta-da! Next time, derivatives.